Here's a solution to practice question 3 from week 3. The first part of this question asks us to produce a scatter plot with the most appropriate variable shown on each axis. So we have two variables here in addition to the index I. Food expenditure, which is weekly household food expenditure measured in dollars, and weekly household income measured in hundreds of dollars. So that actually corresponds to $369 of weekly household income. This one here is $1,855, for example. So which is the most appropriate variable to have on each axis? Well, conventionally we show the dependent variable y on the vertical axis and the explanatory variable x on the horizontal axis. Here we are trying to explain food expenditure, the dependent variable, as a function of income. So that will be the explanatory variable. So we want this one, income, on the x-axis, this one, food expenditure, on the y-axis. I'm going to select that data, including the headings, although that's optional, and then insert an XY scatter. Now there it is there, but you can see I'm facing the same problem as we saw in the lecture, that Excel has by default assumed that the first column of data was the x or explanatory variable and the second column was the y. So we've actually got food expenditure measured on this axis and household income measured on this axis. The title here of income is the same as that one there, and that's because when you're doing a scatter plot like this, often it is the dependent variable y that is of the most interest, so hence Excel gives that as the default title. In class I showed you that you could fix this problem simply by cutting this data, the y data, and then pasting it on the other side, so that now we did have our x variable first and our y second. But another way of doing this is to right click on any data point on the scatter plot, select data. That income series is actually our x and y values. I'm going to edit it, and you can see here that it's, for the name of the series, it's grabbing income. That's what the title we can see. Now the x values, it's referring to column B, and the y values column C. So I could reselect those things, clicking this button and then just highlighting them, but I'm just going to change the columns manually because that's probably marginally easier to do. So I've done that. Click OK, click OK again. And now we do have the household income variable being measured on the x-axis and the food expenditure variable being measured on the y-axis as we desired. Another part of this question asks us to put a trend line or a sample regression line through this data. So we're going to achieve that by right-clicking on any data point, selecting Add Trend Line. We'll go with the default linear. The question also asks you to display the equation on the chart, so there's a tick box option for that. And you're also asked to display the coefficient of determination. Another term for that is the R-squared value, so we'll tick that box as well. You can already see that Excel has done this for me, and in class I showed you that if you wanted to extend, or you could extend this trend line forwards and backwards so it got to the end of your graph by adjusting these figures here. I'm not going to do that because that will then require me to adjust the maximum and minimum values that I have on this horizontal scale. It'll just take too long. So part A is achieved. Part B says you've now got three statistics displayed on your graph. That's this 10.21, the 83.416, and the 0.385. And the question is, what do each of those things represent, and to provide an interpretation of them. I'll flip over now then to a Word document. And I just wanted to briefly show you a feature, or a couple of features in Word that you may not be aware of that I find quite useful. So here in my Word document, you can see all these funny symbols, kind of pie-ish thing, these spaces, that's a tab. And when I'm working in Word, I always have this, or invariably have this feature activated. It basically allows me to see the structure of the document, its formatting, and hence, if you just came across a document or working on a document, you couldn't tell exactly how this line or each of these three lines had been indented. There are some ways of indenting are better than others. If I have this feature on though, I can now see exactly how the indentation has been achieved. The first line, it's been done with spaces, lots of them. This is generally a bad technique, and you can see that that one actually doesn't align perfectly well with the other two. Another way is to use tabs, which is what's here. That's pretty good. And the other way is to adjust the left margin, which you can see up there, which is also an effective way of doing indentation. And both these last two allow you to keep things pretty standard. So if I was working on this document, you would never see me do something like that. If I was indenting, it would always be with a tab or changing the left margin. Down here, I just wanted to quickly show you that there are different ways, different tabs that you can use. For example, this one here, rather than using the conventional left tab, where all the text after the tab starts at that point and then goes to the right, I've set up a tab that is a center tab. So when I hit tab here, whatever I type after that will be centered around this tab that I set up, and similarly on this one. And changing the nature of your tabs is done by this button up here. So that's a central tab. What I have now with one click is a right tab, and I'll just show you how that one works. So I will highlight these two, and I'm going to set up a tab, say about here, that right tab, and now when I type, the text sits flush against the right tab and then spreads back to the left. On the next line, I do the same thing, and I have nicely aligned text on the right. And you could play around with the other options through here if you wanted to. The final thing I wanted to show you in terms of Word formatting is people will often go to a new page by doing lots of returns, which is obvious when you've got this feature on. You can see that that's how they did it. A far better way of getting text onto a new page is just to insert a page break. And that guarantees now that that line, whatever it was, is always going to be at the top of a new page. And back up here, you can see how I got that to the other page. This formatting feature is showing me that it was a page break. If I just go back and take it off, now you can't see how I got the text to the next page. So that's just something to think about when you're using Word. I find it a very useful feature. Okay. Moving on to part B, we were asked to interpret the various statistics that we saw displayed on the scatter plot. So the partially specified form of the sample regression line is this: estimated value of y is equal to estimated value of b1 plus estimated value of b2 times x1. That says if you feed in a value of x, let's say 15, multiply it by your estimate of b2, which is 10.21, and then add on 83.416, which is our estimate of this, that will get us this y value, estimated y value over here. So of those three statistics, we've got our estimate of the intercept coefficient. That's it there, where the regression line is cutting the y-axis. And note that that occurs when x, the household income, is equal to 0. So the interpretation will be that this B1, or estimated B1, is our expected food expenditure when household income is equal to 0. And in this case, the value is $83.42. The second statistic is the slope coefficient, 10.21. And that on the graph is the amount by which this regression line rises when we move 1 unit to the right. So if I go 1 unit this way, the y value should increase by 10.21. Same up here. Move 1 unit this way, the y value should increase by 10.21. So a little bit more formally, this parameter estimate tells us that if household income, the explanatory variable, increases by 1 unit, in this case 1 unit is $100, then food expenditure will rise on average by 10.21, $10.21 per week. And the last statistic is the R squared, which is 0.385. That is telling us, or estimating, the proportion of the variation in Y that can be explained by changes or variation in X. Or specifically, in this case, it says that approximately 38.5% of the variation in food expenditure can be explained by variation in household income. Part C asks a question about whether the data appears homoscedastic or heteroscedastic by looking at this scatter plot. And when encountering somewhat technical sounding words like this, homoscedastic, heteroscedastic, it pays to try and see if you can relate those words or parts of them to things that you already know. And in terms of that root of homoscedastic, homo, you know several words that start with that. So homosexual would be one of them. That means same sex. Homogeneous or homogeneous is another one. This means same parts or elements. And it is the case that homo is a Greek word meaning same. And now all we have to think about is what is the scedastic element? Well, scedastic is also Greek and it means scatter or spread. So something is homoscedastic if it has the same spread or the same scatter. Down here. So I've got that word homoscedastic meaning same scatter. And in mathematical notation, you can see that variance is a measure of scatter. And this expression is saying that the variance is a constant, some number we don't know, but a value that's fixed. And so we could ask ourselves up here, if we were to look at any given point on this scatter plot, does it look like the dispersion or the scattering around the regression line is the same? Well, if we look at low values of X, weekly income, there's very little dispersion around the regression line. Like these things are very close, these data points are very close to it. As the X value rises, we start to see the data points being more and more spread about the regression line. So here's a big deviation. Here's another big deviation, but in general the deviations are getting larger. So I think it would be fair to say that the scatter is smaller when the values of X are low and seems to get larger as the values of X get bigger. So it doesn't seem like this scatter plot is showing homoscedastic data. It must be then that it's heteroscedastic. Hetero means, or the hetero part means different or other. So different or other scatter, small scatter, larger scatter. Part D says estimate weekly food expenditure for a household with weekly income of $1,000. On this graph, that means that you will be looking at this value of x, 10 lots of 100 is 1000. So it says feed that value of x into your regression function and see what the value of y, or weekly food expenditure, is produced. So it looks like that's going to be roughly 180, but we can use this fitted regression line to actually calculate it a bit more precisely. Got that down here. So here's the partially specified sample regression function. Here is the fitted sample regression function, saying that we can get an estimate of y by taking the intercept coefficient 83.4 and adding to that 10.21 times the given value of x. And if we use the value of x that we know of 10, see the 10 being substituted in here for x, we get an estimate for weekly food expenditure of 185.52, which is roughly what we were expecting by looking at the graph. The second part of this question says, would you expect this estimate to be more or less uncertain than one made for a household with weekly income of 2,500? Well, weekly income of 2,500 gets us out around here as an x value. And then when we look at the y values there, we note that some of them are quite a long way away from the regression line. And back to what we said earlier, it seemed like the dispersion about the regression line was getting more and more larger as our x value got larger. So I think I would conclude, because of this heteroscedastic relationship, greater dispersion about the regression line as the values of household income rise, that there's much more uncertainty here. When we're trying to predict what the food expenditure is for someone with a household income that's higher, we have less certainty about what it's going to be than if we're looking at someone who has quite a low level of household income. E takes us back to Excel. And here we're asked to produce a more formal regression analysis using the data analysis tool in Excel. So I will do that using data analysis, regression, the y values, that was food expenditure. So I just did the Control Shift down arrow trick to highlight all those. I'll do the same thing here. Control Shift down arrow. Now note that when I was selecting my data, I included the labels, so I better tell Excel that. And I'm going to produce my output in a new worksheet, which I'll just call question 3 regression. There are some other options that you can select down here. You can play around with those yourself, but for now I'm just going to go with the default output. There is there. I'll just highlight all those columns and double click on the margins to get the margin of the column widths a bit tidier. And what are we asked to do here? Shade the cells in which the statistics considered in B are displayed. Well, that was the R squared, 0.385, remember? There is there. And we also had these values down here. Our intercept was 83.416, and the slope coefficient, which here is getting given the name of the dependent variable that it relates to, was 10.21, I think we saw on our chart. And then finally, the question, part F, says there are 3 standard error figures included in this regression output. Find them and give a brief explanation of what each one represents. So there is a standard error up there, and there are also 2 standard errors down here. And just briefly now, I'll say this standard error is relating to the dependent variable y, or we might say the disturbance term u. So it's sort of to do with the model as a whole, whereas these two standard errors are associated specifically with the regression coefficient, a particular regression coefficient. So this one is associated with the value of B1, the intercept. This standard error is associated with the value of B2, the slope coefficient. Just to conclude, I'll have a look at these things in Word. So our first statistic, the one that we saw at the top, had a value of 89.5. This is called the standard error of the regression, or the standard error of the estimate. And standard errors are essentially standard deviations or estimates of those. In this case, it's the standard deviation of the y values about the regression line. So another way of saying this is it's the standard deviation of the disturbance terms. Those two things are virtually, or they are equivalent. So just looking at our graph, what that's saying is that it's measuring, imagine that for each of these data points we found how far it was away from the regression line. So this distance, this distance, this distance, this distance. So if we take the standard deviation of all of those distances, the answer that we would come up with is 89.5. The second standard error estimate was for the intercept coefficient. We came up with a value of 43.4 for that. And that, now remember that this B1 is something that we're estimating. That's what this hat symbol says. And every time we draw a sample from the population and use that sample data to estimate B1, we will come up with a different estimate for B1. This number 43.4 is telling us the estimated standard deviation of our estimates for B1. A little more formally, I've said the sampling distribution of B1, remembering B1 is a statistic, its probability distribution is called its sampling distribution, and the spread of that is measured by, or one way of measuring its spread is the standard deviation. So 43.4 is the estimated standard deviation of the estimates that we would come up with for B1 from repeated sampling. Note, we only took one sample here and estimated one value of B1. This 43.4 is assuming that we did this many, many times and estimating the standard deviation of all those estimates that we would come up with. The final standard error is similar, but this time for the slope coefficient. It was 2.09 in our regression analysis. And this one has a similar interpretation to the previous one. Again, B2 is going to have a sampling distribution, and this is an estimate of the standard deviation of that sampling distribution. You can think of it as an estimate of how much dispersion or how much variation we'll see in our estimates of B2 from different samples. Right, that's question 3. Hopefully it makes a little more sense after hearing some of that, those explanations.